Ladies, do I have a mic? Yeah, there we go. Welcome, ladies, gentlemen, and smart contracts. I'm Dean Tribble, as he said, and I'm from Agoric. We are a small startup company that has been working on smart contract technology since before there were blockchains, for at least some of the founders of it. And our goal the entire time has been to bring the entire world's economy, all the ways that people cooperate, the diverse kinds of market behavior they have, and enable bringing that online safely. And so smart contracts are the technology with which we want to do that. Now, we're nothing if not ambitious, but we can't do that ourselves. We can't do that with even the help of everyone in this room or everyone at this conference. To achieve that, it's just too big. We need the millions of developers out there in the world that when they get up, when they wake up to solve some problem that they have, they can do so in a way that makes it a decentralized solution. They can take our technology and they can use it safely to solve the problems that they have. And there's some obstacles to doing that. Right? There's some challenges. Who here remembers when web interfaces were fill out a form and click a submit button? Right? Remember that? Yeah? A few people? Oh my gosh. So then JavaScript came out, and we could add event handlers. And now we could suddenly increase the expressiveness of our programs, but it was still something that it took experts to get right. It was fragile. There were security holes, etc. But now, tens of millions of developers every day are building slick, professional, secure, responsive, internationalized applications with a polish that we couldn't have imagined 15 years ago when JavaScript first came out. And they're doing it because instead of building with these very low-level tools, they have a framework. Right? And that framework is crucial for enabling them to succeed at solving these problems. That's how we were able to empower tens of millions of people to solve problems without talking to each and every expert around them. So we need a framework that they can work in for smart contracts, because right now, smart contract world is kind of in that same place of HTML plus a little bit of event handlers. And we need to get to the point where we're building with the equivalent of React or Vue or Angular. And then the other thing that's a big obstacle to millions of developers being able to build our online economy for us is the security model. Right now, in the various smart contracting systems that are available, even experts can't get the security right. And so we end up losing tens of millions of dollars in minutes with essentially no recourse. And to bring all these developers forward, it's got to be safer than that. It's got to be easier for them to do safe composition. The other thing I'll say about frameworks is that they end up being a set of components where, again, all these developers wake up and they're able to put together programs in their tools with their test frameworks and so forth, using components produced by other third parties. Okay, so before we go much farther, I'll say a few more introductory bits and pieces. So what is a smart contract? For a long time, right, our model of smart contract is a contract-like arrangement expressed in source code where the behavior of the program enforces the terms of the contract. So by that phrase, indeed, Bitcoin is a smart contract. But Ethereum and the other smart contracting frameworks gave us the ability to express much richer smart contracts, where we enabled programmers to build their own use cases to solve their own problems. And that's an environment that lets us do more in a decentralized fashion. But there are limitations. In some sense, the Ethereum gave us the opportunity to do all of this, but they inherited some of the legacy that we have from traditional systems. So the main one, and I mentioned it before, is the security infrastructure, right? In Windows, in Mac, in Linux, we have this interface from human to computers where it has what's called the identity-based access control model, right? And I go to a company, I get a few rights, maybe a year later, or if you're good, 6 months later, you get promoted, and I get a few more rights, right? But it doesn't change very much. And it's pretty well understood that the access control list model, the identity-based access control model, doesn't handle dynamically changing permissions very well. Right, so the moral equivalent of I've got a car, I want to lend you my car, I give you my key, you go to the hotel, you hand it to the valet, you go in, you come back out, it's a different valet, the first one went off duty, you get the key, you come home, right? And if it was identity-based access control, instead, I lend you my car by taking your name and telling my car that, Joe is allowed to drive. And Joe goes to the hotel and asks the valet for the valet's name and then realizes that Joe is not, in fact, an administrator on the car, and he's stuck. And now my two choices are leave Joe hanging or make him administrator on my car. So not only can he park it, but he could also sell it. Right? That's the kind of thing that when you start looking at dynamically changing rights and so forth, access control lists tend to end up with either not enough authority or too much authority, what's called excess authority. And in that excess authority is where security vulnerabilities creep, because people are allowed to do things like sell my car that I entirely did not intend. Right? And the same thing shows up in smart contracts. If I have a ticket in one of these systems that uses access control lists, I end up taking your ID, your address, your public key, and I'm going to do a concert ticket, and I embed it in that concert ticket smart contract. And now the problem is that I've given you access to this ticket. You, of all the people in the world trying to redeem this ticket, are the one that's able to do so successfully, but you can't go to the concert. Well, you are unable to sell it. You can't even give it to your best friend because you don't have authority to change the ID, the address that's buried inside of that contract. Now, if I did a bunch more work and added a bunch more fragile security code into my smart contract, I might think ahead and enable you to be able to give it to your friend in the event that you couldn't go to the concert. But it's code that has to be added, it's a source of complexity, and it exactly matches the experience we've had for years in the desktop computer where it's hard to be able to dynamically change who has what rights. And smart contracts, going back to that original definition, are fundamentally about changing who has what rights. If I engage in a sales exchange with you, I'm posting a ticket for you to pay me money, and the smart contract that I'm doing that for is going to transfer the right to the ticket to you so you can get into the concert and transfer the money to me. Right? And the net result is a change of rights. And the whole point of having a system of smart contracts is to make that easy. So what we need is a security model that makes that easy, that matches that behavioral pattern instead of the, gee, I get promoted in a year if I'm lucky. So the identity-based access control model, it bakes in that notion of owner, which is hard. It impedes transfer, it impedes cooperation or composition. It prevents that dynamic change of rights. And the complexity that people need, the epicycles you end up adding onto these smart contract systems in order to be able to recover some of that dynamism, all is complexity that ends up being a source of bugs. So, there is a solution. There's a solution approach. This comes out of a history of secure operating systems. Originally, the Kikos operating system, the Midori operating system at Microsoft, now arguably the most secure operating system on the planet, SEL4, is in this object capability model, or OCAP model. And formally, allow me to introduce to you, a transferable, unforgeable authorization to use the object it designates. And you need to understand that if you're building an object capability system out of crypto behavior, if you're building the operating system details with memory mapping and all that sort of stuff. But when it surfaces in a programming language, which is where, when we're building smart contracts, you will primarily be encountering this, it's just an object reference. And so object capabilities at the programming language level is the kind of thing you've experienced in Java, in C#, and in JavaScript, where you have an object reference, and then we build patterns of using just simple, straightforward object programming to recover security behavior, to implement security policies, or in our case, to implement market policies and market behavior. So we'll give some of that. And if you think about it, going back to that car example, my having the key to the car is like an object reference to the car, and I hand it to you, and now you can drive the car, right? So let's talk about a simple example. So on the left, I've got a entry and exit counter, right? Remember, I was doing this concert. This is a very simple example done in JavaScript where I want to be able to, I've got a clicker when people come in the gate, I got a clicker when people leave the gate, and I want to keep count. On the right, I create one of those, and then I'm just calling the entry guard and saying, hey, here's your clicker. Now, for people not familiar with JavaScript, that pattern of counter.countEntry on the right, that's just taking the method and pulling it out as an object. So that's, don't be confused about that. It's just I'm passing an object to the entry guard, and that's the clicker that he can use. Same with the exit guard. I pass them the exit guard. And the important thing here is, in a fairly natural way, in an expression in the language, not only have I provided the entry guard with the clicker, but I've provided only the entry guard. So I have provisioned and I have done a secure transfer that no one can intervene in. And that entry guard, when he goes off duty, can hand it to Jane, the next entry guard, and now Jane can do the clicker as more people come into the concert. So that's very simplified, and it looks sequential. In fact, the way we do systems, it's primarily around doing asynchronous messaging, as I'll talk about in just a moment, but we'll stick through examples for this more simplified approach, just so you can see the concept of the duality that the title talks about of contracts and rights. So what are we building? Okay. Originally, when we were doing smart contracts and smart contract systems, it was between individual machines. This was before blockchain. So it's cryptographic protocols, cryptographic messaging between machines where two parties wanting to engage in commerce could find a source they can mutually rely on, deploy a contract there, execute it in order to engage in an escrow exchange of money for tickets or what have you. And blockchains end up creating new machines out of agreement rather than out of silicon. So you can think of Ethereum as a machine with the compute power of a cell phone, but with vastly higher integrity and assurance of correctness, right? And so we have several different machines. Solo machines would be, the wallet on my cell phone. Small quorums would be permission chains, Hyperledger, etc. And public chains would, of course, be everything from Bitcoin to Ethereum to Polkadot, etc. Okay, and before I go on from here, Agoric will be using this technology, but a lot of people have already innovated there. Our primary value add is above it, and so we're using Substrate to implement our chain and expect to deploy as a parachain on Polkadot because, problem solved already. Why not use that? Okay, and then above that, we have a runtime layer where we have VATs. That's just our notion of like a virtual machine for an object system. So those are islands of sequential programming in a sea of asynchronous messaging. And on top of that, we build our object system. We have an object system with the familiar, approximately transactional model that JavaScript programmers are familiar with. If you've used browsers or programmed in Node, there's an event loop, message comes in, action happens, you go to the next event. In the contract model, in VATs, we enhance that where message comes in, hey, bid on this auction. It computes from contract state expressed in simple JavaScript objects. It computes a new state and set of messages out like, okay, transfer the money to my bank account. And that's a transaction. And so these VATs are transactional units inside of which are objects. Those outbound messages are delivered asynchronously to other VATs, other contracts running concurrently with this. But all of the programming model, just like in the browser, looks approximately synchronous. And again, I'm going to stick with that for my examples. And then above this, and then of course messages are delivered asynchronously, yes. And above this, we have the contract framework with smart contracts and electronic rights building each other. And I'll talk more about that. But that's what enables us to have a rich ecosystem, or ecosystem, as I spelled here, a rich ecosystem of contract components. And that's what I'm going to focus the rest of my talk on. Okay. So here's a simple example, and this is all stuff that's done in JavaScript. Oh, I should point out, I say JavaScript. It's done in a secure subset of JavaScript, which is much of what we've been building. And I'll mention later the proof of concept of those intermediate layers, but I'm going to stick at the contract layer here. Okay, so we have a mint, which is essentially a way to make a new currency. The ledger is represented as purses with some of the currency, and the operations you can do on a purse are get a balance or deposit a purse from that same currency into your purse in that currency, right? So if I don't want to be able to deposit apples into oranges, I can only deposit oranges into oranges, right? So on the right, we've got a use of it where I'm giving this concert. So I just make a new currency, which is concert tickets. And I'll get to the issuer in a moment. Let me come back to that. But now when I want to return someone a ticket, I just mint a new token in that currency, and now I've got a ticket for the concert. And if I was going to return 4 because they were doing a bulk purchase, I could mint 4 new tickets, and they have 4 tickets for the concert. Or, alternatively, if I've got some other arrangement that I've built in this language, right, it's very straightforward. Let's say I've got a receive ticket method that I'm supposed to invoke on Carol to pass her the ticket. I can make a ticket, and I can just pass it as an argument. Now, remember I mentioned that here it looks synchronous in our system. It's actually asynchronous. And Carol might be in the same blockchain. She might be in a different blockchain that I'm linked to asynchronously. She might be on a wallet, on a single machine, or on a permission chain. It's all the same from the point of view of here. It's just a matter of latency difference. Okay, so that's the simple example where these are just JavaScript objects that I'm building with. The problem, let me go back for a moment. The problem is they're just JavaScript objects. I've got a pointer. If I've got a pointer to a ticket and I pass the pointer to you, now we both have a pointer to the ticket. You don't necessarily have it. I could go and use it before you do. So how do we deal with that? Well, we deal with that with patterns of objects, right? So we don't need to add new magic. There's a pattern of object, and that's where the issuer comes in. Oh, thank you so much. So an issuer acts like a verifier for tokens or for objects in a particular mint. So in the previous slide, I had the concert issuer, which if I'm creating the concert, I would then post in the venue. Here's the concert issuer. Here's the thing by which you can verify that you have an honest-to-gosh ticket instead of some random forgery. So Carol receives her ticket. I could have sent her anything. It might be a ticket to a concert. It might be, a cookie. I don't know. And so what the get exclusive operation on the issuer does is it does 2 things simultaneously. It takes a purse in the issuer's currency and creates a brand new purse, transferring all of the rights that were in the original purse to the new purse. And that only succeeds if the original purse was actually in that currency. If I've got an issuer for apples and I pass you a purse of oranges, it fails, right? And what that means is, if it succeeds, not only do I know that I, in fact, in this case, got a concert ticket, but I also know that I now have exclusive access to that concert ticket. Nobody else has access to that concert ticket. And so I have now gone from just passing a reference in an object-oriented programming language to actually transferring the right to that concert ticket. Right, so it is a transfer, and I have received it. So in this case, Carol received it, verified that she has it. Given that she has, she returns the payment to me. And so my code down below was I minted the ticket, I sent it to Carol, I got the payment back, I deposit the payment in my account, right? And so that would now be the conclusion of a sales transaction. Of course, I'm an idiot here because she might not pay me. And she's got the ticket, and now she's off, and she goes to the concert, and I never get my money, right? Or she gives me less than I'm supposed to have or whatever, right? So open coding, low-level stuff, again, it's a lot like event handlers, wired in at the very early days of JavaScript. You can do it, but it's programming without a rope, right? And this is where frameworks start to come in. So what do we have as a framework for that? We have what's called an escrow contract. Most people have heard of escrow. I've got a ticket, you've got the money. I put my ticket in escrow, you put the money in escrow. It tells it, yep, I've got both goods. It swaps, you get the ticket, I get the money, right? And it doesn't do that delivery until both sides are available. Okay, so here, that's exactly what I'm doing. I create the escrow contract. I send to Carol her side of the escrow so she can post the money for the ticket. And then I say, I'm willing to exchange my newly created ticket for money in my account equal to the ticket price. And if she provides money equal to the ticket price, then she'll get the ticket, right? And then what Carol does is the opposite side of that. She's delivered the ticket facet or a ball of mud, whatever I sent her. How would she know? Well, she knows because that very same get exclusive works for escrow agents, right? So now she knows that she has exclusive access to the side of the escrow on which one pays, so she doesn't have to worry about paying and then someone steals the ticket, right? She has exclusive access, and then she says, well, I'm willing to give you this purse of money as long as you give me my one ticket. And if that works, then she succeeds, the escrow closes, both sides get what they want, and neither side was at risk. Right? So now I've got this escrow agent contract that I used in order to complete a sale, and it provided me what we call a market safety property, where, if you think of software engineering as a history of safety properties, type safety, memory safety, concurrency safety, and now market safety, where, in the frameworks we provide developers to be able to build user interfaces, nowadays they're really not worrying about dangling pointers in C. They're whipping together components quickly in React or Angular, and that set of bugs that might be a dangling pointer, that's just off the table, right? That's not something they have to worry about accidentally expressing. Concurrency bugs are the same way, right? Reentrancy is an issue that resulted in the DAO bug. You'd like a system that it's not that you have to be smarter, because 20 million people aren't going to be smarter than the people who built this stuff. What you need is a system where, you just can't say that. And that's a safety property. Well, here you get the same kind of thing. If I use an escrow agent to exchange my goods, I can't accidentally not get paid and lose my good. I either get paid or I get my good back, one of the two. Okay. So that's where the duality comes in. I talked about a couple of contracts, right? Smart contract where I created a brand new right out of whole cloth, which was the ability to come to my concert, right? So contracts create rights. If I created a new auction contract, the seat at the auction to be able to bid is a brand new right that I created, right? And then some contracts manipulate rights or exchange rights or trade rights. And so that escrow exchange that I showed you, it's, the right to participate in the escrow is a new right, but mostly escrow exchange is about transferring some other rights in the system around. Similarly, I've got escrow exchange. If I wrote a small smart contract to take my ticket, which remember is now this first-class right that can participate in any of these activities, I can write a smart contract that if you call exercise, will transfer the ticket to you for a fixed price until the end of the month. Right? So until the end of the month, you could say exercise and pay a fixed price. That's effectively what's a covered call option, if people are familiar with that from stock markets or what have you, but I can do that as a fairly small contract. The way we do that in our system is, of course, you hit exercise, it figures out the price, and then I've already got an exchange mechanism. I'll just instantiate a new escrow agent in order to engage in the trade that happens. And so the actual delivery of the underlying good when you call escrow on the covered call is orchestrated by a brand new escrow exchange contract, right? That just exists for the life of that exchange. But that covered call is a new right. Right? And one of the important things about a lot of these systems, again, back to the security model where I have to put your name in, when I wrote the concert ticket or when I create the covered call, I put your identity in that contract, and now the only thing you can do with it is exercise it. But in a system where it's just an object, it's a first-class participant in the economy. So I can take that covered call, and I can turn around and sell the covered call using another escrow exchange or using an auction or a marketplace, and I can sell that to you or sell that to someone. And that's the duality, where contracts make rights and contracts participates in the rights that they make. And if we do that right, we can build a much larger ecosystem where we're building a network of contracts on top of each other in the same way that our physical economy has businesses built using each other's services. So that's where we get those reusable components. And similarly, when we build an auctioneer in our system, again, in some of the simple examples we see of auctioneers, they have all the money handling code to return the money to the losing bidders. In our system, new bidder comes in, I just instantiate a brand new escrow agent, their bid goes in there. Now, if they're the winner, I give them the good and the escrow agent delivers it, but I can't give a good to any of the other bidders that weren't the winners. That means that even if I have a bug, I can't steal their money. right? So we've got that means I get to use this same escrow agent in a wide variety of circumstances to be able to rapidly compose interesting business relationships and new contracts that I can then further use to build other businesses. So this is what enables building an ecosystem of components and building a framework that people can rapidly develop interesting contracts. So, object capability model enables the dynamic transfer of rights, which is crucial for people to be able to intuitively understand what they're doing. And in all of this, you didn't see me checking whether I had permission. I just sent Carol the escrow agent, and I know in my simple invocation that I've successfully delivered it to Carol, I've authorized her to do it, and no one else can get at it. And I did that trivially in my expression of the communication and interaction I had with the parties I want to be in business with. Being able to build these things where contracts by default are creating first-class rights enables this ecosystem of reusable components, enables frameworks, and enables the future economy to build contracts on contracts. So these are some of the key ingredients that we will need so that the millions of developers out there are able to build interesting contracts in the same way that they can build interesting UIs right now. So we're at Agoric. You can come look. You could tweet at us. We report our progress weekly on Proof of Work newsletter, if people are familiar with that. We have a proof of concept implementation of the layer in the middle that does the VAT execution, replicated deterministic computation of JavaScript code, secure JavaScript code inside of our environment. I invite you to download that and play with it and start building smart contracts on our system. Thank you.
So we're actually running a bit early, so we have as much as 10 minutes for questions.
Oh, okay.
So I'll have them update the timer, but take as many questions as you like.
Okay, and if you want to put my slide back up?
Sure. Well,
I have a tease on the next slide.
Oh, sure. Put the slides back up, please.
So, questions? Let's start over there. Oh, yes, you have to throw a mic ball. And can you put my slide back up?
Hey, thanks for the talk. So when I hear secure JavaScript, I obviously have some questions. Well, the first question is why not use something like TypeScript? Because JavaScript doesn't have memory safety issues, but it has other issues of that modern languages don't necessarily have just null references. Where if you use something like TypeScript, then you can enforce nullable types and yeah, type systems can be very helpful for developers in general to assure safety and correctness, and which I assume is the goal here.
Right. So I think the language you said is why not use something like TypeScript?
Yeah, correct.
Okay, great. So first off, we may, right? The important thing is in a distributed system, you can't guarantee what the other guy's running anyway, so you must dynamically check all of your types. So architecturally, TypeScript is useful for developers, and we totally value it a lot, but the underlying what actually is your security model, even for TypeScript, it's JavaScript. Now, we actually have, for our contracts, we have a subset, which is also on our GitHub site, called Jessie, a subset of JavaScript. So we have a secure subset of JavaScript called Secure ECMAScript that we've been in the standards body, the JavaScript standards body, for 10 years, driving all the elements that go into that. And then we have a much, much tighter subset called Jessie that our formal methods partners think we can actually do a sound type system for, and then we would do something TypeScript-like. So I don't have any problem with types, but fundamentally, TypeScript is not a sound type system. You cannot rely on it for security and correctness. You can rely on it for helping development process, and it's great, but it's not enough for smart contracts. And so we need a model. And the other thing is, the language is way less important than the security model, right? So replacing the surface syntax, even going from Solidity to EWASM, the security model is the EVM model. That's the important model for Ethereum. In this thing, the important model is the objects and figuring out what operations they do. The operations don't matter if you can trivially prove that guy cannot get access to my bank account. I don't care what his code does. He can't touch my bank account, and I'm done. Right? And so you end up having much simpler ability to reason about the reference graph rather than the type graph. And so that's enough more powerful that that's our primary focus. More questions? I'll tease you up here, by the way. Behind there is, I kept talking about the escrow agent, so that's the code, from at least some version of our implementation proof of concept. 20 lines of JavaScript that implement, of secure JavaScript that implement an escrow agent that works across all kinds of resources. So anyway, sorry. More questions? I see a question in the back there, and then you.
When you say secure subset of JavaScript, can you, with just a few sentences, explain what you mean just by,
Sure.
like, very, very simple sentences?
Sure. It is an accident of history in the way the standards of JavaScript came in, partly, that there's sort of a user mode, system mode separation in JavaScript like in operating systems. So the JavaScript Standards Committee doesn't get to talk about the document in Windows that you get from HTML. That's often WC3. It just has a model of JavaScript where, it's running in a host environment and there's some privileged object that gets handed in, which is the document or the window. So in the smart contract world, we don't have that document in Windows. So in JavaScript, without our security kernel, as we call it, one JavaScript program loads another. The loaded JavaScript program can crawl around and steal all the secrets and change everything in the JavaScript environment that loaded it. We've been working over time to add features to JavaScript, proxies, promises, weak maps, a bunch of these other features, to be able to produce a security kernel so we can do featherweight compartments such that I can load a JavaScript program into that compartment and it simply cannot escape. There's nothing you can express in the language, so I don't care what your code is, nothing you can do can escape out of that compartment I loaded you into. And I can then give you individual objects that you can invoke, like the ability to load your contract state, and now you can execute and do whatever you want to compute a new state vector, but you can't reach inside and look inside of other contracts and so forth. So it's featherweight compartments. And that actually we built in collaboration with Salesforce and others, and it's now up there underneath the Salesforce Lightning platform, providing the same kind of compartments for their world of third-party applications. So it's getting some battle testing as well, which is great. And you had a question? Right in front of the camera. Yes, you? There. I keep forgetting the mic has to wander around. I want to see them throw the mic. That's what I want to see.
Hi. Yeah, thanks for the talk. I was just taking a look at some of your GitHub repos, and including the playground and everything. I'm just wondering, is all of this going to be, is all of this open source, and as developers, is this going to be like free forever to use all the components and everything? And yeah, just how that's going to be structured.
Yes. So it will all be open source eventually. There will be some pieces that we will open source when we're very close to deploying our chain, so we get to capture some of the network effect. But yeah, absolutely, it's all open source. So for example, that security kernel, we open sourced in the very first 2 months of our operation in order to get it out there so people can use it to secure the web, right? We were driven to do this in order to be able to lock down, to deal with some of these Web 2 security issues, because in Web 2, with some of these attacks, the Princeton no boundaries attack, people have heard of that, where libraries were loaded that got to steal off of various drugstore sites patient data and prescription data. So horrific HIPAA violation. But in Web 2, they steal your data. When those go to Web 3, they're going to steal your money. Right, and so we need to close those security holes before we get very far down the line. And so a lot of these technologies we were already building in order to enable the world to be a safer place for all kinds of applications. And so yeah, absolutely, everything will be open source.
Thank you. So I kind of have two related questions. One of them is, can you expand on the interface between Agoric and Substrate? And then the other one is there a network of Agoric, or is it a pattern that you layer on top of something that you're running on something else?
So the answer to the latter one is, all in reverse order, the answer is yes, there is a network, or there will be. So we've done a lot of innovation at a lot of different levels, but there's people who've been working on blockchain consensus mechanisms for a really long time and have a lot of great ideas there. And Polkadot is a big one. We started looking at Substrate when we were first working on building our own chain, and looking at Substrate as an implementation vehicle for building our own chain. And we're looking, and it's like, oh, there's a bunch of great ideas there. They're complementary to our ideas. They support ideas. We can integrate well. And so my goal, our goal, is to get the contract model out there as soon as possible, as widely as possible, so we can start enabling a whole new class of developers to be able to build smart contracts and to do so safely. And so the shortest path to that, from what we can tell, is to build on parachain, or build on Substrate, and be able to go out as Polkadot, as a Polkadot parachain, so that they're providing the security for or rather the underwriting or the assurance of consensus, while we're providing the model that all us mere mortal programmers can understand and succeed at. And so we're excited to be working with them, and they've been helping us, start to implement the core representation and that sort of thing. And so we'll be going out as a testnet on Polkadot. Now, when I said yes, because originally and architecturally we do secure messaging between machines, that chain, that parachain, is a machine, and it can perfectly well extend our uniform fabric over to other permission networks running our model, other parachains running our model, or a layer 1 chain running our model. So, we're going to start there. We're really looking forward to it. We're very excited about the Polkadot ecosystem, but we don't intend to stop there. We intend to work with a lot more partners to enable that same model to be able to bridge across multiple chains. And that's, Polkadot's been all about bridging across multiple chains for a long time as well. So that's entirely compatible, not just with their technology, but also with their ideals. And so they've helped us articulate some of those too. So it's a good partnership.
Yeah, hi. Just over here. Yeah, thanks for the talk. Great approach, love it. Great work. What I'm asking myself is, since Polkadot is really trying to give this very generic approach to build up and deploy blockchains, have you yet identified some restrictions or some prerequisites that would come for us to be able to integrate Agoric on top of some Polkadot network and parachains?
So we do have restrictions, some of which we need, some of which we like. I guess, so finality helps a lot, right? And so finality is important. It's not crucial, but the thing is, when I send a message, when I send money, and it's probabilistic, okay, I know my outside risk. When I send a message, that then has some action in the real world, ship the medicine, right? Now, having a probabilistic reversion, it's like, crap, now I don't know where the medicine is anymore. Ship the samples, or whatever it is. That's bad. So you really want finality if you're in a system where the results can cause action in the real world, as opposed to just money transfer. The other thing is that we prefer an account model rather than a UTXO model, because it means, we expect, many of the team come from building large-scale systems with lots of customers and lots of transaction volume. And we expect smart contracts that are getting a lot of messages, such that you'd like in a block to be able to have more than one message to the same smart contract. And if you've got a UTXO model underneath, you need a lot more coordination so that there aren't two messages to the same contract that say, start from state 1, go to state 2, and now they conflict on what state 2 is, when those were two independent operations on the smart on that contract. And so the account model turns out to allow you to better pack multiple operations on the same contract into the same block. Thank you all.